from Module 15.4, Segment Relationships in Circles. Essential question: what are the relationships between the segments in circles? Shortest answer is with regards to the property of chords, chord-chord product theorem, so it's dealing with chords only, secant-secant product theorem, and then secant-tangent product theorem. And this reveals all the relationships between each other. So these are the three um, theorems that you need to know. All right, right off the bat. So those are the three. So first up, chord-chord product theorem. Basically, if two chords intersect inside a circle, so if you notice C, D intersects chord AB at point E. All right, good. Then the products of the lengths of the segments of the chords are equal. So basically what they're saying is AE times EB should equal CE times ED. And let me just do that. There you go. All right. So let's look at an example of what I'm talking about. So let's solve for x, all right, which is AE. Now we have two chords here. We have AB and CD, right? Now, again, AE times BE should equal CE times ED. And that's according to chord-chord product theorem. So AE is x, BE is 3, and that should equal CE, which is 6, times ED, which is 2. So how do you get rid of a multiplying 3? Divide what you do to one side to the other. So x equals 6 times 2 is 12, and 12 divided by 3 is 4. So x should equal 4. So that's the idea behind chord-chord. So example 2, same situation, except we have to solve for GI. Again, we have two chords, right? We have KI and HJ. So we know that GI times KG should equal HG, or GH, times JG. Now, GI is X, KG is 6. So notice how you have one chord, right? Just kind of mentioning this. Should, equal the other chord, right? So if you guys notice that. 6 times, or X times 6, and then GH is 9, times JG, which is 8. So again, you should have 6x equaling 72, right? Divide by 6. And you should get 12 for x. Plug it back in, right? And you should get, well, 12. So there you go. All right. So that's the concept behind chord-chord. Now, here's the first year turn. And what's really weird is they don't give you a certain length. So let me try to make up something real quick at the top of my head. That's a good one. Yeah, why not? All right. So ED is 8. Okay, so go ahead and solve for that. Solve for x, and let me know what you got. All right, so let's focus on some definitions. A secant. So that's a new thing, a new definition. A secant is any line that intersects a circle at exactly 2 points. A secant segment is a part of a secant with at least 1 point on the circle. So here, AE, for example, right? That's a secant. All right. Now, at least a secant segment is a part of a secant line with at least 1 point on the circle. So, for example, BE would be a secant segment. Okay, it has at least 1 point, right, on the circle. Now AB doesn't work because it's 2 points, right? So BE is the secant segment. Now, a secant segment that lies on the exterior of the circle with 1 point on the circle is called an external secant segment. So this is the external. All right, so that's the external. And then I guess we could say the secant segment could be inside or outside, but more explicitly, external is the one on the outside. Now, secant segments drawn from the same point in the exterior of a circle maintain a certain relationship that can be stated as a theorem. So basically, that's what it says here. And then it just says that AE, so your entire secant, okay, from here to here, times BE, which is the exterior secant segment. Okay, so I'll mark AE is the whole thing, right? And BE is the outside, the exterior, should equal CE, which is again is the whole secant, secant line, right? Times the outer part, which is DE. All right, so that's the secant product theorem. So basically, it's the whole guy times the outer guy, and that should equal the whole guy times the outer guy. Okay, and that's basically the simplified way or just shorter way of thinking about it. So let's look at example 3. Let's solve for x. All right, so we have the whole guy, right, AC, which is x plus 5, right, times, again, we're doing AC times AB, right, which AB is the outer guy, and that should equal AE, which again is the whole guy, times the outer guy, right? So again, AC times AB, and then AE times AD. So AE times AD. So we have x plus 5, which is AC, and then AB, which is 5. And that should equal AE, which is the 6 plus the other 6, right? Which is really just 12, times AD, which is 6. So we have, I'm going to go ahead and distribute. So we have 5 times that x, 5 times that 5, get 25, right? And that should equal, let's see here, we have 6 plus 6, that's 12. And 12 times 6, you should get 72. So we have 5x plus 25. Let's solve for x. Subtraction property, what you do to one side, do the other. We have 5x equaling, let's see, that's 4 carry over because we have to reduce, right? There you go. So you got 4 and 7. Go ahead and use division property. This is not a real pretty. Oh, yeah. Okay. No, yeah, that's right. Okay. I don't have a really pretty answer here. That's weird. You got a prime number there, and ugh. Okay, so that is horrendous, isn't it? Okay. Still, still checks out. I mean, if you're not sure if it checks out, you can always plug it back in to make sure, to double check. So I'm going to do that real quick. All right, let's do that. I think it does. Those fives cancel out. 47 plus 25. Yeah, 72. Checks out. So yeah, terrible improper answer, but totally works. All right, example 4. So let's see. We have SP or PS, right, which is the whole secant line, times the exterior, which is RP, which is just 6, right? So RP, and that should equal UP or PU times the exterior, which is 7, which is TP. UP times TP. UPTP. All right, so say that 10 times fast. Freak out the sub. All right, there we go. So PS is 8 plus the 6, right, times RP, which is 6. That should equal UP, which is X plus the 7, times TP, which is the exterior part. That's 7. All right, so let's go ahead and work on um, simplifying. So it's 8 plus 6, right, 14. Distribute. And then we got 4 times 6, right? You should get 24, carry the 2, so you got 84, equaling 7x plus 49. Get rid of the plus 49, subtraction property. So we have 7x equaling 30 here if you want. You could do that, right? So we have 5, carry, there you go, 3. And then division property. And you should get 5 equals x, or with the symmetric property, x equals 5. All right, there you go. So that works. All right, so your turn number 2. Again, whole guy, right, times the little guy equals the whole guy times the little guy. So go ahead and try that one out and see what you get. All right, so next thing is a tangent segment. So we already know what tangents are, right? They hit here, and according to the radius, right, they're a right uh, angle, right? They only hit once. There's the tangent segment, which is a segment of a tangent line with exactly one endpoint on the circle. So that would be right here, CD. That would be an example of a tangent line. Now, do you guys notice how there's a secant line and a tangent line? So here's your secant line, AC, and then you have a tangent line. So once you have a secant and tangent, you should think literally secant tangent product theorem. And that basically says AC, all right, AC, which is the whole guy, times BC, which is the external secant, should equal DC squared. All right, so let's go ahead and show you what I mean. So notice this is my tangent line, okay? And then I have my secant line, which is the x plus the 2. So basically, let's work on this. So it's the secant line, which is x plus 2, right? The whole thing, times the exterior, which is 2. And it should equal the tangent, which is AB, squared. So AB is 5, so squared. So again, BD is the whole secant line. The external is BC. And again, it should equal AB, your tangent line, squared. All right. So BD is x plus 2, BC is 2, AB is 5. Go ahead and work on the distribution property. Subtraction property. Looks like we're going to get a weird answer again. There you go. Division property. And again, it looks like it's a weird answer. In your calculator, right, you should get 10.5. So that would work. All right. If you want to leave it as improper, I'm not going to freak out. All right. So it's okay. You can leave it like this sometimes. It's totally up to you. All right. Engineering, that would be a better answer, but that's at the very end, just because you don't want to round too soon in your process. All right. So here's another example. Again, we have the secant line, right? And then we have our tangent line. And again, just like how the theorem, the secant tangent product theorem stated, we have AC, right, the whole secant, times the external, which is BC, right? So again, the whole guy times the outer guy equals the tangent line squared. Okay, so AC times BC should equal DC squared. So AC again is the 6 plus the 4, right? The whole secant line times BC, which is 4, and that should equal DC, which is x squared. Go ahead. Let's start simplifying. And get rid of the square root, right? And you could probably leave this as a, we got the 4, we got the 10, and you should know right away that the square root of 4 is 2. So we have 2 square root of 10, and that should equal x. You can get a decimal and do that if you want, but 2 square root of 10, it's more exact. All right, so your turn number 3. Go ahead again. Think secant tangent. You have a secant, you have a tangent. Set it up as the theorem says, and then just solve for y. Here's your homework, page 823 through 825, numbers 5 through 8, and then 10 through 15. Let me know if you have any questions or concerns, and yeah, have a good night.